So intermediate value theorem. Calculus, oh my goodness, they are known for theorems, I feel like. There are lots of theorems that we accumulate by the end. And this one we're talking about is the intermediate value theorem. Okay, first of all, we've been talking about continuity, so it does relate back to continuity. It's one of those things that often has to be met for a theorem to be true. So continuity of a function will prove to be an important characteristic in many theorems for our course. In order for theorems to be properly applied, we need to meet the certain conditions. Namely, the if part, called the hypothesis, must be satisfied before we can apply the then part, or the conclusion, or consequence of the theorem. So the whole idea of the if-then, I'm sure you guys have talked about those in science classes or whatnot. But if something is true, then something else can be true or could be true type thing. So in this lesson, we explore our first existence theorem. Existence theorems allow us to draw conclusions about a function's behavior on an interval without precisely locating the behavior. So a lot of calculus theorems are just, if this is true and this is true, then this must exist. And that's the idea of what we're looking at here. Okay, so intermediate value theorem. IVT. Folks, even on the AP test, you can use the abbreviation IVT. Anyone that speaks calculus is going to know that IVT is the intermediate value theorem. Okay, so the IVT says that a continuous function on an interval cannot skip values. So using if-then statements, it is the idea, if a function is continuous on a closed interval, and the endpoints do not equal each other, then f of x takes on every value between f of a and f of b on the interval. Or another way to say it, if we know a y value, say y equals k, that resides between the two endpoints, then we are guaranteed at least one value, c, between the endpoints that generates that y value, such that f of c equals k. So I know I kind of just read through those, but general idea, and this is, we're going to show this in example 1. But if a graph is continuous on an interval, so from point A to point B, that means we know continuous, the idea that it connects, right? It may go up, it may go down, who knows where it goes, but it's going to connect from here to here, not having any gaps. That means what we're saying here is that every point in between the beginning and the end has to exist. So you can pick any x value in that interval, and there's going to be a y value on that graph, because the graph is continuous. So it's all based on, if a graph is continuous, then there has to be a point in the middle for everything. Okay, that's what we're saying there. I think easiest thing here, let's try and look at a few graphical representations. I know that's what, my words only make so much sense. I get it. The picture should hopefully help a little bit. So graphical representation of the intermediate value theorem and its corollary. So the first part, a continuous function on an interval cannot skip values. So right here, how do I want to do this? I'm going to pick a point A, or a point above A, and I'm going to pick a point above B, okay? And I'm going to connect them. I don't know if I'll like that later or not, but it gets the idea. And the idea now, okay, is that, so here's A, yes, or I say here's A, then I start to go to B. Oh my gosh. And here's B. So then over here on the y, the y value when x equals A, we refer to as f of A. The y value when x equals B, we refer to as f of B. Okay? Trying to get to where the pieces are going to make sense. This random function I drew, which I'm not crazy about how I drew it, but this is our f of x function. And let's see, do I have all the basics I want on there? I guess I'm trying to look at, and I do have all of the other, the dotted lines extended here. Okay, I think I have everything. I'm making sure I have everything I want on there. But if you go back and look, it says if a function is continuous on the interval and the endpoints are the same, it takes on every value. Let's see, where's the one that involves c? Oh, it's the other one. There's one guaranteed value c. So I'm going to pick a point, c. The requirement is that c has to be a point between a and b. Does it matter where? No, it doesn't matter. I'm going to put c over here. Okay? So c is a point between a and b. What we're saying is that f of c is required to land on this graph. And it has to land on this graph because it's between a and b. And this graph is continuous between a and b. So right there, notice it landed on the graph, and I have an f of c value. Okay, so it just says that if c is between a and b and this function is continuous, f of c must exist. There has to be a y value in this interval. Okay, that's what we're saying. Now, this is a has to be less than c, has to be less than b. So c has to be between a and b. And if that is true, f of c has to be between them. In this case, because I drew this as a decreasing function. Okay, I drew this as a decreasing function. Could have worked as an increasing function, but if you notice in this case, f of a is the bigger one. So f of b is the smaller one, so we can write that f of b is less than f of c is less than f of a. Okay. So I'm not sure how much sense that's making quite yet, but it's a very basic, the idea is very basic if you let it be. Are we there? Maybe? Kind of? No?
I think I understand, I just don't think I know how it's going to. Like, I understand what you just said.
I understand.
Okay.
Yeah, but if you give it to me in a problem, I'll have it.
Okay. And that's obviously where we'll go to here in a little bit, is past that and looking at some of the ways that we could use it. Okay. Coming up in a random, I don't know. It does sometimes come up in random problems where it can help you prove something to get to a farther point in the problem, but just starting with the basics today. Okay, the other piece we're going to look at here, an important outcome of IVT is that it can be helpful in finding zeros of a continuous function on an interval. So, just right there referring to how are we going to use this, when am I going to use this, this is a place that it can be helpful here. And that is the idea that, okay, we have A and B, but I'm going to put one of my points, I'm going to pick A, to be down below. So then that means that f of A is going to be down here. Okay. And then I'm going to put B up top, or up higher, in other words. The key is A is below the y-axis, B is above the y-axis. Fair enough? So now if we have, okay, and I forgot, that means this over here is f of b. So now the point I'm trying to make is that, okay, if we have something connecting these 2 points, and again, it doesn't necessarily matter what it is, where it goes, other than these 2 endpoints are connected. If you have this point at A and this point at B connected, what we know for sure is that at some point, what's this graph have to do? It has to cross the x-axis. So there has to be a 0 there. Okay? And so that is point C. And so the idea that a 0 must exist. Okay, it must cross the x-axis. So let's see, what have I not labeled? This is my function f of x. Notice in this, f of b was positive. F of a was negative. And so with that in mind, 0 falls between those. So the idea that f of a is less than 0 is less than f of b. And this point here, I labeled it as C, I guess, but it is the point C comma 0. Okay, so that's one of the ways we'll use it, is we can say that yes, at some point on that interval, this graph does equal 0. Okay, this function does equal 0 because one endpoint was negative, the other endpoint was positive. Okay, this was an example of an increasing function. It could be done just the other way as well. Okay. I think I got all the information I want to state there. So let's get to looking at some ways that we can talk about this, use it, etc. And there's, a variety of things, but part of what we're doing also today is just working your understanding, trying to get you to a point of better understanding. Okay, example 2. Ask us, does the intermediate value theorem apply on the specified intervals for the piecewise functions shown below? Be sure to explain completely. So, is there a value of x equals c on the interval -2 to 5 such that f of c equals 1? So this doesn't say anything about IVT or anything. Just, is there a value on the interval from -2 to 5 such that f of c equals 1?
Yeah.
So where are we looking? -2 to 5. And what does f of c equals 1 mean? Okay, that it crosses through the y value of 1. And where does it cross through the y value of 1? Something like that, right? Okay, and now they don't ask for a specific value, just is there a value x equals c on the interval such that f of c equals 1? And I just have written in my notes, yes, c exists. C exists on the interval -2 less than or equal to x less than or equal to 5. And I could have used interval notation because they use interval notation, but yes, we've talked about it, you see it. Okay, we don't have to, yeah, it looks like it's about 3.5, but we don't have to state what that x is. Now, B. Does IVT, so does intermediate value theorem, guarantee a value of C on the interval -2 to 5 such that f of C equals 1 and justify? So according to the theorem, is it guaranteed to exist?
Wait, no.
No, because it's not continuous.
Okay, so up here we spotted a value exists, yes? We spotted a value exists because we looked with our eyes and we see it. Okay, we physically can see it. This one, so specifically according to IVT, does that guarantee it? So if we couldn't physically see the graph, what's the catch here? It's not continuous. So no, IVT does not guarantee a value of C on the interval -2 to 5 since f of x is not continuous. Now, I honestly have that whole piece written down. And I'm going to write it down so you just get a feel for it, but that's kind of your official AP lingo, if you will. Like what, you would need to get your details in. So I'm going to say no. IVT does not guarantee a value of x equals C on the interval -2 to 5 since f of x is not continuous on the interval. Okay. So that's just an example where the value can exist. We're not saying the value doesn't exist. We're just saying it's not guaranteed according to intermediate value theorem. Okay? Look at the next graph when you're ready. And look at question C. Is there a value of x equals C on the interval 1 to 6 such that g of C equals 3? So what do we say? 1 to 6. Such that g of C equals 3. Is there a value? Okay. Where's the value? It's over here, yes? Your g of C equaling 3 is over there. But what they ask us, they specifically asked us on the interval 1 to 6. And there's nothing in the 1 to 6 range that works. Okay, so no, there's no value on 1 to 6 such that g of C equals 3. There is no value on 1 to 6 such that g of C equals 3. And that's just eyeballing it. Nothing to do with the theorem, right? Now, D. Does the intermediate value theorem guarantee a value of C on the interval 1 to 6 such that g of C equals 3 and justify?
Yes.
So what's different than last time? Between 1 and 6, it is continuous, yes? But there's another piece that we have to look at. We have to look at continuous and, so it's continuous and let's see, f of a does not equal b isn't the one, but it takes on every value between f of a and f of b. Let's look at what f of a and f of b are. In other words, in this case, what is f of 1? F of 1 is 1.5 maybe. What's f of 6? -1. What's the catch?
3 isn't between those.
3 does not fall in between the y values of -1 and 1.5. Okay? Only the values between -1 and 1.5 are guaranteed. Yeah, could this graph have been drawn differently and go up and then down? You know, it could. But it's not guaranteed, is what we're looking at there. Okay? So, no. IVT does not guarantee a value g of c equals 3, and I'm just going to state my endpoints. Since f of 1 equals 1.5 and f of 6 equals -1. In all honesty, by stating those endpoints, to a math person, you have proved it. Okay? To a person that understands calculus, you have proved it because you just have to be able to, oh, 3 is not between those. Okay, so I know 3 is not guaranteed to be in the interval. But if you want to, I have written in kind of in parentheses, and 3 I put -3 does not lie between -1 and 1.5. There's probably better ways to put it too, but okay. 3 conditions that are necessary to apply the intermediate value theorem. What have we been talking about? First one was f is continuous on the interval a to b. Okay, you can't apply IVT, just doesn't apply if it's not continuous. Just stop there. Okay. We didn't really use this one, but it mentioned the fact that the endpoints cannot be equal. So in other words, you can't have f of a and f of b being on the same line. And that comes with, you know, we don't know what the graph does in between, but we can't guarantee it does something. So f of a cannot equal f of b. And then the one that we just came across is that f of c has to fall between f of a and f of b for this to work. So f of c must be between f of a and f of b. Those are your 3 conditions as we proceed through that have to be true. Okay, continuing on, let's try and get through, we should be able to get through example 3. Okay, so apply the IVT. So basic example to use it, apply the IVT if possible on the interval from 0 to 5 so that f of c equals 1 for the function f of x equals x squared plus x minus 1. Okay, what was our first condition that I just listed? 3 conditions. We're going to talk about each of them. The first one was?
F is continuous.
Okay. Is f continuous?
Sure.
Yes, because?
There's the C. Right?
There's no asymptotes.
Yeah. What is this? It's a parabola, yes? That kind of falls into the category of any math person knows it's continuous. Because a math person knows it's a parabola. And so one option is you could write, I just have written on mine, f of x is continuous on all reals. You could also write that polynomials are continuous everywhere. Okay? And I'm sure I looked at some examples that she had, but now f of x is continuous. I'm going to do something different here. Continuous on, you guys remember this fancy R? Yeah, it stands for all real numbers. Okay, so that's just saying f of x is continuous on all real numbers, or on the real number set. Okay, again, it's a polynomial. I would probably mention that it's a polynomial, but I'll do that on my next one. The other piece, or piece 2, was that f of a cannot equal f of b. Well, how do I know that f of a doesn't equal f of b? I need to find them. Okay, and I'm not even necessarily, we're not even going to look at the graph here, because sometimes you might get a graph you don't know what it looks like. But what is f of, what do I mean f of a? That would be f of, interval is a to b, so f of a is f of 0. What's f of 0 going to be? -1. Plugging it in, right? So f of 0 equals -1. And f of, what's b? F of 5 is 29. Right? Just plug it in. 5 squared plus 5 minus 1, 29. Right there. What did we just show here? F of a does not equal f of b, right? So we stated this continuous. We showed that f of a does not equal f of b. Is this going to work? What's the other part we have to make sure of?
F of C is between F of A.
So f of c is between, so what is f of c? 1. What's 1 have to be between?
0.
Has to be between what f of 0 and f of 5 are, which means it has to be between -1 and 29. Is it between -1 and 29? Yeah, 1 is between -1 and 29. Now, this is where I have my fancy answer written out. And I'm going to say, by IVT, there exists, okay, that word keeps coming up because it's an existence theorem, a value C such that f of c equals 1 since, and I'm just going to put, you could put it as, what I would probably say is f of 0 is less than or, do I want to say equal to? I don't know. F of, what were we talking about? F of c, which is less than or equal to f of 5. Okay, or you could also say it as -1 less than or equal to 1 less than or equal to 29 because those were the values we were given, right? Or that we came up with. Okay? And I'm going to say on the interval 0, less than or equal to C, less than or equal to 5. Okay? So, those are some ways to do it. Okay? Stating that that value is between the other values is important there. So, okay. What do I have? Page and a half tomorrow? Would it be beneficial for me to come in here? It might, mightn't it? Okay. What I will probably plan to do is come in here. I can't stay all the way up till noon because I have to be back in there. But what we get. Maybe I'll look through and pick. Because I don't know if I can do all these examples, so I'll pick some out and try and get a couple in, and then you guys will have some more time. Okay.